Okay, so let's get started. It's my pleasure to introduce you guys Professor Jingfeng Wang from Georgia Institute of Technology. Jingfeng received his bachelor degree in theoretical and applied mechanics from Peking University. Then he received his master degree in computational fluid mechanics from the same university. And then he moved to the United States and got his PhD from Massachusetts Institute of Technology a couple of years ago. He was a lecturer at MIT for a while, for a few years, and then he moved to Georgia Tech in 2020, and now he's a professor, associate professor at Department of Civil and Environmental Engineering. I know Jingfeng for 2 years during my postdoctoral experience at Georgia Tech, and I want to add some personal statements about who he is, beyond these kinds of degrees and honors and awards. I think Jingfeng is unique in the sense that he has the courage and patience to just challenge the status quo and approve the scientific norms with a special unassigned curiosity. And so he's very patient, and he just follows his own scientific conviction. And I'm really glad that he accepted our invitation as part of our Warren lecture. Please join me to congratulate him, and please get started. Thank you.
Yeah, it's a truly honor to be invited to speak at this Warren lecture series. It's also fortunate to work in the exciting area of hydrology, that we have seen great transformation of the subject of the science. What I have experienced myself is the hydrology has transformed from local scale study to global scale research that happened mostly in the last 30 years, which I happened to work as a student and then as a researcher. So here, the top figure that shows the typical situation that we're dealing with as hydrologists, perhaps 30, 50 years ago. This picture is one of my favorite. That's what we're looking now. And this transition is made possible, in my view, mostly by the rapid advancement of remote sensing technology that provide global coverage of observations, many processes that's most relevant to hydrology study. So now, so you will see here is what happened if you go to the field experiments before, years ago. Now is what happens now. So the Earth is monitored by a suite of satellite here provide observation for mostly the hydrologic study, climate study, etc. So this is the situation that we're dealing with now and working the age of remote sensing area. Compared to the rapid advancement remote sensing observation technology, the modeling improvement is relatively slow, if any, at least in the fundamental level. And this improvement hydrological modeling scale has been lagging the advancement observation technology. Here is what caught my attention when I was close to finishing my PhD study. It is the study called International Intercomparison of Land Surface Parameterization Schemes, known as the FIPS, that was going on in 90s for about 10 years last century. Here, this is the study that's very important. They set stage for the later development hydrology modeling. So what the important conclusion from this multi-team study is that they found that no single land surface model is capable of capturing all features of surface energy balance under all conditions, which is a very strong statement. They tell us something that fundamentally weak or wrong in the models we've been using in doing hydrological simulation and forecast. So that's really one of the major motivations for my research after this. So let's look at what could go wrong with this existing traditional modeling tools that we've been using all the time? Some of the, I'm sure, these approaches or methods still being used nowadays. As we know, for any land surface scheme, so-called, as you know, is the program that dealing with the hydrological process. At the core of all this land surface scheme is the model of fluxes of energy, water, and the gases, the greenhouse gases like CO2. So any land surface scheme have to deal with those calculation of fluxes. So here is what being used so far. One approach is called the bulk transfer model that we're all familiar with. So here we have the sensible latent heat fluxes expressed as some gradient scalar variable, either temperature and water vapor density, expressed in analogy to the electric circuit. And this model is simple, intuitive, very convenient use. For some areas like oceanography nowadays, that's the only way being used to model fluxes over like oceans. And the second one in hydrology is so-called the Penman model. Penman model is also a fluxes model, widely used in hydrology and other areas. So this is the latent heat sensible heat flux. So what difference of Penman model from the bulk transfer model is that Penman put conservation of energy. So on this bulk transfer model, it's considered one big advancement in modeling hydrology, especially the evapotranspiration process. So I'm gonna say more about that. So these two approaches, when we look at it carefully, we see they subject to some major weakness. So this is what I summarized, what this commonly used model, the weakness with this model. I highlight the major one in the right color, and the secondary to that using different color, just to emphasize the importance of this weakness of the existing model, and where we can tackle those difficulties and get improvement. For the bulk transfer, in my view, the major weakness is lack of conservation of energy, because the bulk transfer model does not have energy constraint. So there's no mechanism to make it satisfy the most fundamental physical principles, conservation of energy. And also for the Penman model, it does conserve energy. Well, it's only valid for a specific case, which is the wet soil. So it's good, conserve energy, but dealing with special case of saturated surface. And then we look the other weakness of the both approaches is, for example, both model is based on actually the bulk transfer parameterization of fluxes. It requires use of measurements of so-called bulk gradient of either temperature, of water vapor variables. But as we know, the bulk gradient has subject to larger measurement of modeling error, because you're looking at difference of two close variables. So once you do that, you lose accuracy. Also, these empirical or semi-empirical bulk transfer models of fluxes, they use so-called transfer coefficients. This transfer coefficient used to parameterize using the variables including wind speed and surface roughness. And those variables or parameters, data, are also subject to larger measurement models, errors. And also, when we look at the remote sensing data, as far as I know, there's no way you can measure wind speed over land surface using remote sensing technology. It doesn't exist. Although you could do some measurement over ocean using the roughness as a surrogate, but they also subject to large error. So that's the difficulties I would think associated with the traditional model of fluxes. again, once this, this parameters has some uncertainties, now we're totally bringing to the fluxes that we're trying to get. And also, look at the theoretical basis of the bulk transfer model. It is, at the best, it's a semi-empirical, as viewed as first-order closure of Reynolds decomposition of fluid flow. So, as we know, it also carries some empiricism. And this weakness, any of them, is very hard to correct or improve on, because they seem to be fundamental. So, but it also opens opportunities. So we have to tackle those issues at the very fundamental level using untraditional approach. So that's what I'm trying to do. That's what motivated the work I'm going to tell you next. So I have to choose a target, what I'm starting from. And the obvious choice, as you will imagine, is the evapotranspiration process. So as we know, evapotranspiration plays a unique role in Earth system process, because then it couples water cycle, energy cycle, and the carbon cycle. So at the center stage of the Earth system process, and so anyone studying Earth system at some point will deal with ET process. As we show later, and eventually we get something actually buy one, get two other free deal. So it's a good starting point. So where we start from? We look at bulk transfer, look at payment model. What do we know from that? What does those model tell us about the process itself? When I look at that, it doesn't tell us much about what happens, what's the fundamental physics underlying the ET process, considering it's a such unique, important, complex process that couples water, energy, carbon cycle. There's lots going on behind it. While the model we use to simulate or forecast this process is based on such simple and even rudimentary understanding of the process, it's mostly just conservation of energy, nothing else, what I can see. So the question I ask, again, I hold the view that if we want to improve model in a dramatic way, in a fundamental way, we must understand better the underlying physics. So the question I ask is, are there more fundamental principles underlying ET process other than the conservation of energy itself? So one of the idea we had years ago is the so-called maximum evapotranspiration hypothesis. So this is the idea coming from our understanding of the ET process as a very special physical process involving phase change. What I think of this is I always think it in the context of surface energy balance. So as we know, the surface energy balance for the land surface can be written as the radiation, net radiation, including all the solar and long-wave radiation from the atmosphere terms, that will be equal to our partition into the evapotranspiration sensible heat flux that change the temperature of the air, and the ground heat flux that change the temperature of the soil. So there's I think of it as a computation of the three fluxes of the three processes for the same resources, which is the net radiation. Think of this. If you have a certain amount of radiation, where this radiation energy goes, it goes to, of course, it goes to all the three processes. Which one does that favor? It likes more of, likes ET or sensible ground heat flux more than the other. So I think of, if you imagine a situation, assuming you change everything else being equal, you just change the temperature, surface temperature. And so we know if you change the temperature, everything being equal, both ET, sensible ground heat flux will increase, because there seems to be more energy coming into the system. They will go out. But there's only so much they can increase because the energy is fixed. So at some point, if you keep changing energy, one of them will win out. So that's what I think. Imagine what happens. Which one win out? I would think E, because E is very special process. It plays a unique role in this partition process. So I hypothesize that the E will be maximized under the condition that everything else being given under given environment. So this idea seemed to give us some clue of how this, what other physical process is going on. Principle, they can help us to better understanding the land-atmosphere interaction. So this, as we all, the ET process itself is well understood what's going on, what affect ET rate. Mainly there are four, I call the basic element ET physics. We must, for ET to happen, ET is defined here as an energy-driven phase change process of water. I emphasize this very much in my class to my students. When you think of ET process, think of energy, think of phase change. So not only some classical textbook focusing one of these four fundamental processes, especially the transport. Many people tend to think ET as a transport of water vapor in the boundary layer. Actually, it's not. It is the energy that is driven force, and the phase change, it is what drives everything. So if you have a good ET model, you must including the effects of energy source. In this case, we're looking at natural process. Radiation is a source of energy. A supply of water. So we'll have to make sure the surface, the Earth's surface being the soil, other type of land surface, must have a liquid water or solid water there so that the phase change water can happen. And then one of the main physical factor there for the phase change is the temperature. It's what we know the fugacity is the tendency of liquid solid water tend to change phase, become vapor. So that's, as we know from thermodynamics, that's characterized by the temperature of the evaporating surface. And then is the transport mechanism. The evaporated water vapor have to be carried away by the mixing process, by the wind, by other in the boundary layer, so that the phase change process will continue. So in that, if we agree on these four basic elements of ET physics, then theoretically we should be able to write ET as a function of these four variables. Although for now, I do not specify, I don't even know what it's functional for, but I know it must be able to, I should be able to do this. And with this setup, I could do a test. I'm now trying to give you all the math derivation of how the test is being done. I just show what is the general idea to do the test of whether this hypothesis of maximum ET rate is true or not. So what we do is, if we could formulate this function in such a fashion, I want to find out what would happen if this is maximized given the constraint energy balance. That's what we're trying to do. And the rest of it is straightforward. You should take the derivative to find the stationary point and figure out that stationary point is indeed the maximum. So we could test that equation as a necessary condition for ET to be maximized using the data. I did test it. I did many tests. I will not show it here. I just tell you what I see is those conditions indeed is satisfied if you're using the field test. So give us experimental evidence that this is consistent. Nothing is proved because no matter how many examples, you cannot prove a principle, a theory. It can only be shown they are consistent unless you tell me and they give me a counterexample. It's not true. what's more interesting is that I know ET is maximized, it has a special role in the land surface atmosphere interaction. What about the other two? Is sensible heat more favored when you do the energy partition if there's no water there? So what I found is if there's no water, none of the sensible ground heat flux has advantage. Nature seems to treat these two in an equal footing, in an equal way, so that neither is either maximum or minimum, but it does the partition of the radiation over the dry soil case is not arbitrary. It reaches a so-called stationary point, but this stationary point is called a saddle, so it's neither maximum nor minimum. So it's a special, but not the extremum principle. So again, this is, it tells us there's something going on underneath the energy partition over the Earth's surface than just conservation laws. So this is the demonstration of there more to be understood for the process of energy partition. So with that, it provides important clue for the model development I'm going to focus next. So from this exercise of research, we learn few things. Okay, the ET does play a special role in the land surface atmosphere interaction. It has an edge over the other heat fluxes process. And then this is the more important conclusion or the lesson I learned from this study is that the surface energy budget is controlled by the water and thermal condition at the surface. It has a very important implication to the model I'm going to show you next. So it shows if we look at land surface condition, it should provide enough information for us to figure out what the partition of the energy should be. However, if I do this way, do this theoretical test of this hypothesis, either maximum ET or stationary heat fluxes over dry land surface, it tells me why it goes like that, why the energy partition looks the way it is. But it doesn't tell me how or how much. Since the test of the hypothesis, the formulation of the hypothesis test is so-called non-parametric, means I do not use any specific model of ET sensible ground heat flux. So regardless of the model is, I am just assuming there's a general relationship between the fluxes and those state variables, especially the water condition and the thermal condition of the surface. So it's good in one sense, but bad in the other, that it doesn't give me the value. I could not tell you exactly, I know it's maximum, I cannot tell you how that maximum is. So in hydrology of any subject, if you cannot do the quantitative prediction, it's considered to be a not so useful result. So there is demand to go one step further to, I know what's going on, but I want to do the quantitative prediction. So again, I'm listing here the ET physics I'm trying to include in the new model of the heat fluxes, especially ET. I want to include radiation energy there. I want to include the soil moisture effects. Things we know that's the characterization of the water supply elements in the ET physics. I also have to consider boundary turbulence, because that was make the transport of water vapor in the carrying away the evaporated water vapor. I must include the thermodynamic water phase change. So that's what's the physical essence of the ET process. It's a phase change process. And for the vegetated land surface, I have to consider the plant physiology, like stomata closure, opening that will affect the transport of water vapor in and out of the leaves, tissues, etc. So all this has to be included. So we have to include all this physics relevant to the ET process, while using the classical method models won't work, won't enough. So what I've been thinking is to use the more contemporary theoretical tools to develop the new model of ET, as well as you'll see the other fluxes. It's buy one, get two free deal. So eventually what come out of this effort is called the maximum entropy production model. So this model is built on several theoretical tools. One of the one of the most fundamental tools of this model development is it uses the Bayesian probability theory. This is a big topic. I won't get into any detailed discussion here, but here is viewed it, if you're familiar with the topic, there are several interpretations of this idea, Bayesian approach. I view it as calculus inductive logic as a quantitative manipulation of information. That's what I need to do the model development. And then we need to use information theory, especially the concept of entropy. So the entropy here is actually so-called the information entropy. It's not the familiar thermodynamic entropy we know very well. Although there is inherent link between these two concepts. In fact, the thermodynamic entropy is a special case of the more general information entropy for a certain system, physical system. So that's what that plays a central role in the model development. So keep in mind that entropy is information entropy. And then we use the so-called maximum entropy principle to assign probability distribution, which is one of the major theoretical framework in the Bayesian analysis being used in all the science engineering subjects for years. What's the most recent development is the application of the general maximum entropy principle to the non-equilibrium system that we're working with. So as we know, non-equilibrium system means there's a transport going on, whatever the transport process is, either energy or mass or momentum. So the application of the maximum entropy principle to assign the probability distribution of the system to the non-equilibrium system is the so-called maximum entropy production principle. Although the name is misnomer, it's very misleading, actually even bad, because they gave many people a wrong impression and confused people a lot. Again, we're not getting to that, but I just want to give you an outline what's underneath this development of this new type of model. Again, we have to use the theoretical theory for the boundary turbulence. It's well known that boundary layer atmospheric boundary turbulence, only mature theory for the atmospheric boundary turbulence is so-called the Morning-Obukhov similarity theory. If you are working in similar area, you probably know this well. If not, don't worry about that for now. So I give you the general outline of what's going on, what it takes to develop the new type of ET and heat flux model that drastically different from the familiar classical model we are familiar with. So there's a long way to go from the very fundamental principle of Bayesian theory, information entropy, like maximum entropy. Maximum entropy principle, maximum production, entropy production principle, etc. In the end, this is what the formulation of the model. We come up with something called entropy production function based on this information entropy theory. There's a long story. I won't be able to go through the process here. It is expressed in terms of the energy fluxes squared divided by the corresponding so-called thermal inertia parameter. This thermal inertia parameter is a characterization of the transport process associated with that flux process. For example, if we think of ground heat flux, which is the heat conduction in the soil. It's nothing, there's nothing mysterious about that. We all know very well. So how do we characterize heat conduction in the soil? We know the familiar parameter will be either thermal conductivity, thermal diffusivity. Equivalent parameter for that is so-called the thermal inertia, which is the so-called composite composite property, thermal property of the soil. Is defined as square root of density, specific heat, and thermal conductivity of soil material. So it's another physical parameter of the soil. And here is the thermal inertia of the associated with sensible heat flux. So we're defined based on the same definition of thermal inertia, except the thermal conductivity there is not molecular conductivity, it's turbulent conductivity. A more familiar term of that is called eddy diffusivity. If you use eddy diffusivity, define the thermal inertia associated with turbulent transport, turbulent fluxes, you got this thermal inertia parameter well defined. And to parameterize eddy diffusivity is subject to fluid mechanics, turbulent fluid mechanics. And there's many ways of doing that. One of the common parameterization of that parameter is using so-called Morning-Alpokov similarity theory. I mean, the only mature theory being used in study atmospheric boundary layer turbulence. So I'm following that, although I did a little bit revision of that theory to fit this purpose of this model development work. And what's more tricky is the thermal inertia associated with the latent heat flux. Itself is, because latent heat flux, not really the heat flux, it's a water vapor flux. But we think of here, we're looking at E as energy flux. So water vapor is a mass flux, so I have to make the connection between the two. There's a way of, there's some intuitive argument how to make the connection. I showed it in the paper how you do that. I'm not going through here. You probably won't be interested in that details. This energy, this entropy production function has another name, or has another interpretation. It quantifies the so-called irreversibility of a non-equilibrium system. So for any non-equilibrium system, the natural trend is for the system to evolve towards a potential equilibrium. So how far away of this non-equilibrium system from the potential ultimate equilibrium system can be characterized by so-called irreversibility, how irreversible the process is. It's a familiar concept in thermodynamics. So here it is the quantification of this irreversibility of the non-equilibrium system associated with this heat transfer process. So the minimize means we're looking at system as close to the equilibrium as possible. So equilibrium system has zero irreversibility. So the minimum means we have the non-equilibrium, there is transport, but system in such state that will be close as possible. So that's the physical interpretation. Although, again, I have to emphasize this entropy is information entropy. So what comes out of all these efforts is this. It's the new model of ET, as well as all the other heat fluxes using this new theoretical framework. So it's expressed in three equations. The first equation gave us the sensible heat flux. Here, the input variable, there are three input variables. One is net radiation and surface temperature, and surface specific humidity. It tells the water vapor condition right over the evaporating surface. So if we know that, that's the characterization of how much evaporation happened, or how much water has been phase changed into a water vapor. And then the second equation is how this latent heat, ET, related to sensible heat, relates to coefficient. I give you a coefficient expression next, through a very simple linear relationship. And the third one, just the conservation of energy. You can get that from the third component of the energy fluxes here. Is the G. If it's over land, if it's not over land, you could over any lake, ocean, water surface, also known ice. It is the material heat conduction in that layer at the surface. So that gives the solution of this energy partition over all kinds of land cover types, whatever it's soil, it's vegetation, water, snow, and ice. It gives the full package of the land surface energy budget. And the model solution also including so-called the B function. The B function, if you look at here, it is the inverse reciprocal Born ratio. We are all familiar in hydrology. Expressed in terms of dimensionless parameter given in this form. This sigma is dimensional parameter expressed in terms of surface specific humidity divided by the surface temperature square. So this characterizes the land surface or whatever surface of thermal and water condition. And the effects of that on energy budget, on energy partition. The others coefficient are the physical parameter. For example, lambda is a latent heat vaporization, either liquid water or solid water. So either the fusion, either the what is called latent heat vaporization of liquid water, or the sublimation. It has a higher value. And Cp is the heat capacity of the air. That's what we're all familiar with. And gas constant and water vapor. So you see this parameter include all these fundamental physical processes associated with the phase change process. Water vapor, liquid, solid, and also the temperature and the fugacity parameter characterizes how much water vapor being diffused out of the evaporating surface. So this is the full parameterization of model formulation of this MEP model. And to me, it doesn't look more complicated, at least than the Penman model, but it does have advantages using fewer input variables. If you're familiar with the Penman model requires at least 6 input variables. But here, at most, we need 3 here. So that's one of the obvious advantages of this new type of model for ET process. Also, once we get ET, we'll get all other fluxes as well. So that's what I call, I got 1, got 2 free deal. The ET physics, let's look where the ET physics being included in the model formulation. Radiation energy through the energy balance equation. So it is the obvious, easy to see. Soil moisture. Soil moisture, how does soil moisture, what role soil moisture plays in this model? It plays a role in this surface-specific humidity. As we know, how moist, how much water vapor density of the surface depends on how much water, soil water, liquid water in the soil. So there is a well-defined relationship between soil moisture and the specific humidity of the soil surface. And also to a lesser extent, it can be through the effects of thermal inertia. As we know, thermal inertia of the soil mostly depends on the soil properties, soil mineral properties. But if you have water in the soil layer, they will also change the soil thermal inertia parameter to a certain extent, although not as sensitive as the effects of soil moisture to surface-specific humidity. In fact, I know before, this is one of the way people doing remote sensing of surface soil moisture. Just look at thermal inertia. But the difficulty is there's the sensitivity. At some point, they lost the sensitivity or the ability to detect some small change in soil moisture. Boundary turbulence is parameterized through the thermal inertia, through the eddy diffusivity parameter. And the thermodynamics of water phase change through this non-dimensional parameter called sigma here. And plant physiology, again, it is through the surface-specific humidity. Because how much the stomata opening and closure affects the transport of water vapor from the subcavity of leaf tissues to the outside, to the boundary layer water vapor content. So effects of that will be reflected in this surface-specific humidity, although the model itself not directly including the stomata effects. But here is the idea. Whatever the effect is, in terms of the energy budget of the partition of that region, what matters is the surface-specific humidity. So it's beyond the model formulation itself to look at the other effects on the surface-specific humidity. What's important is if we know the surface-specific humidity, regardless surface type, that's always need to model the fluxes, heat fluxes. So let's go back to see whether the weakness I pointed out earlier has been overcome. Indeed, if the lack of conservation energy associated with the bulk transfer, now we close the energy budget because we use energy budget, conservation of energy or surface energy balance as one constraint, an essential constraint here. And Panman only valid for saturated soil. Here we could deal with full range of soil moisture conditions through the surface-specific humidity. The idea is if the soil is dry, totally dry, then QS is 0 because there's no water vapor coming from phase change of liquid water from the soil. So S is 0. I don't show you that the formulation. I don't say anything there, but in fact, if you put QS to be 0, you get automatically ET to be 0. So that's consistent what we know. And then we have the measurement error of bulk transfer gradient, and the model input variables do not include any bulk gradient or any gradient variable at all. So it only uses the surface variable. So avoid that the measurement error. And then we have uncertainties of the wind speed, roughness. We do not use that either. And also the model doesn't have any tuning parameter as well. So in my view, those major weaknesses have been overcome in this new model. In terms of application, the application mainly have two main categories. One is the so-called flux retrieval algorithm, either in the field experiment or remote sensing, because they use a simple, less demanding input variables. It's more convenient to use, especially for remote sensing. Second, it can be used as a physical parameterization of any hydrology or other climatology, meteorology, or coupled land atmospheric ocean models. So I'll show you some of the applications. Here is the application at the field scale as a flux retrieval algorithm, also as a test of the model. So we have here this observed fluxes compared to the MEP predicted model using the three observed input data, surface radiation, net radiation, temperature, and specific humidity. So you compare the E and H and G terms. So they agree very well. I mean, that's the first example I looked for myself when I did this model development test. And then you have the second, test the second side. It looks just as good as the first one. Also for the canopy surface, again, this is also has excellent agreement. And I always actually couldn't believe that agreement, the level of agreement. And also I tested it from the limited data I have, and this type of work is still going on. More people are using this to test the model over all kinds of land surface type. That's for snow. You could for the sea ice. That's the only data I have at the moment. I'm doing the model development. We have the water surface as well. Water surface is more challenging. I hope I have an opportunity to talk to you more about this later. And this is for the field. And you can look at the global scale using truly remote sensing observation data of net radiation, temperature, humidity, etc. So here is one of the work we did recently with the students. We did a test of the MEP model using truly the remote sensing observation, and compared to so-called analysis, just a collection of all the land surface station measurements. So you can see these two comparison. It looks very much in agreement as far as I can see. And also, not only for land, but also for ocean, although the ocean is not focus of this here. One of the trivial application in the modeling study is use the MEP as a potential evaporation model. So potential evaporation model is the one that's being used in hydrology study, especially related to climate system. And there, the most commonly used is called the Panman-Montes for the vegetation. I use the MEP PET model is simply by setting the surface specific humidity at a saturation level as a function of temperature. So what compares to, it gives totally, I would say, the identical result. But they use much less input data, just net radiation and surface temperature without using wind speed, air temperature, air humidity, surface roughness, all this complicated. Later on, if you want to parameterize the canopy resistance, you have to use a set of other parameters and make it even more complicated. So then the most recent application is use the parameterization scheme for the so-called force restore to model land surface temperature and soil moisture that used as a boundary condition atmospheric models. So we use that to replace the G term as a dynamics of surface temperature by the MEP model in terms of the surface temperature itself, also dynamic equation that can solve very easily to make the prediction. Actually, we compare the observation with the MEP force restore model. It agrees the best compared to any other scheme of the ground heat flux, classical way of doing this force restore model, if you're familiar with that. And the other topic is to use this MEP as a sea surface fluxes schemes, which usually, again, is always use the bulk transfer in existing model. We use the MEP model to parameterize the sea surface flux, which is the key driving force of so-called Maiden-Julian oscillation. Is one of the well-known climate system over the Pacific and Indian Oceans at the seasonal time scale. So it does give much improvement, which is quite encouraging. So because meteorologists stuck here for quite a long time. So it provides another way of doing the improvement. So I'm closing my talk by saying a few conclusions. So there are more physical principles underlying hydrological process than just simply water energy balance. I encourage everyone interested in exploring more to seek more fundamental principles underlying. I'm sure there are more there. So it's great experience to do that, and I'm sure they will be rewarding as well. Also, I think the MEP model has more. It's a promising approach for modeling hydrologic cycle now, because of the theoretical advantages and the practical one as well, because it uses fewer input variables, especially suitable for remote sensing application, because the input variables and MEP model is the remote sensing does the best: radiation, surface temperature, humidity, etc. Not the gradient, because remote sensing cannot make a surface gradient at all. So with that, I would like to, again, thank Professor Ibn for inviting me here. Thank you being with me today. And this research has been going on for many years. So they've been supported by several federal agencies over last, I will have to say, 20 years. So this is some of these projects that are supporting this study. So I will stop here and take your questions.
So I have one question, but I wait to see if you guys might have any question.
Your MEP model looks like a point model. I don't see how you can scale it up in terms of upscaling for being able to interface into global scale models.
Well, that just had to be tested. Whether it works at the average sense, it does. As I show the global maps of that using this approach, compared to other model doing the aerial analysis, it does.
So that sounds like an empirical test.
Well, you could call it empirical, but it does have a basis. If you have a homogeneous uniform, because fluxes is an additive quantity. You could divide it into different areas with a unique property and do the area average or summation. You could get, that should work. Yeah.
So I a very rich talk. There are lots of really interesting things in there for me. But I have a question about the very first part of your talk about how the evapotranspiration has the edge over the ground heat transfer and the sensible heat transfer. Isn't there a physical, logical reason for that? Because you said that the ground heat transfer and the sensible heat transfer depend upon the temperature, and if you have a phase change operation going along the sides of that, that's going to take all the heat away without raising the temperature. So it seems obvious from a physical point of view that you'd expect that.
Excellent question. That's a question I asked myself. Why ET is so special? The reason, I think, is this. If you think of a thermodynamic system, you have a so-called microscopic constraint. You have certain energy. So what's the microscopic configuration of the system corresponding to the same microscopic property? If you have ET, if it's maximized, it corresponds to the maximum number of microscopic configuration of the system for the given macroscopic property. So that's why. So as we know, why the system evolves towards the equilibrium, because the equilibrium system for the same, say, energy constraint has the maximum number of, or largest number of microscopic configurations. So that's what makes system more reproducible. So that's the idea behind it. Yeah.
Any other question? So I have one more, and we will wrap it up. Do you think, Jingfeng, that we can apply these models for short wave and long wave radiation separately?
If you look at the formulation, I have to go quickly. For the water and snow ice surface, which is a transparent, the energy balance actually itself, it only involves long wave radiation. Because the short wave radiation for the transparent media balance itself. So that's what makes a difference. So the model formulation is separate for the transparent surface and non-transparent surface, just because the energy balance equations have different forms over the two different types of media. Yeah, but eventually the energy comes from the sun, no doubt about that. Right? Okay. Yeah, it enters the final solution through the formulation I give you. Although I don't have the details, time to get the full detail of that.
Okay.
That's important fact. That's an excellent question. That asked by everyone.
Any other questions? So let's thank him again. Thank you so much for taking.
Yeah, thank you.